Good. Whoa. I see. Good morning. Wait a minute. That's crazy. Good morning. Okay, that's crazy. Good morning, Mohammed. Good morning, Michelle. Good morning, Lunar. What? That didn't work. Hold on. And why is that? Wait a minute. That's weird. That should. Okay, we'll try that in a second. But good morning, Jalila. Good morning, Nadine. Good morning, Mohammed with the crazy double. Good morning, Michelle with the double. Good morning, Luke. And good morning, Lunar with the double. Double lunar. That's like Mars, Phobos, and Deimos. But why is it lunar not? Wait, this is not lunar's. All right. I don't know what that's about. That's weird. Um, Something's wrong with that seat is like, oh, the immersive view is. That's bizarre. All right. I don't know what that's about. Maybe wait, sorry, it doesn't matter. It's not worth time. Oh, okay. That's what that. Oh, okay. All right. Also, wait, sorry. I don't mean to not be showing video. I keep doing that. One thing I've learned, people, that's really weird. We're gonna obviously start doing physics. You know, if you have that animated avatar going, which I'm all for. I mean, obviously video is the ideal, like really being here is the ideal. And I'm really noticing a difference in the class that I never get to see, that it really does make a difference. But here's the other point. If you ever do that animated avatar, which I think is at least a step up from doing nothing, do you know it actually makes a difference whether you click show video or not, even if you have in other words, if you have the animated avatar going and you click show video, then it really does mimic your motions, for example, smiling weirdly. Whereas if you don't hit click video, then it just does like an Animal Crossing thing. Not paid advertisement. Just saying. I mean, that's just sort of, I don't know. I just find that interesting. But okay, let's do physics. Obviously, um, Monday. So you had your lab, right? I saw you in your lab. So you're rolling along. So that's great. Um, Maybe very quickly. Oh, and good morning, Josh. Sorry, I didn't see you. Good morning, Josh, and everybody, obviously. Oh, and who else did? And Alicia, who was here very early, by the way. Totally noted. Sorry, I should have said hello to you. I didn't see your picture, but I know you were here very early, which I appreciate. Quick. I want to get to like the material. I love this material that we're getting. But are you okay? Is a lot like in a quick word? Like I know you have 2 weeks to do it. I know. I know like there's stuff and stuff, but basically are the technical aspects of the lab working okay? Like, are you able to upload your movie into Logger Pro? Have you gotten to that stage? Are you able to make red dots even if you haven't finished making them? Like, do anybody just quick like, yes, thank you, Melody. Awesome. And thank you. Oh, and awesome. Thank you, Jalila and Nadine. And I think Lunar, thank you. Okay. Um, okay. So like you're basically okay. Because as long as you're technically okay in the lab, and I mean this honestly, as long as like you feel like you're able to get the data, your mind might be swimming with the implications or the intellectual like theoretical mathematical aspects. That would not be a surprise. You would not be the first. It is a big and important, but definitely hard, like new lab. If you're, as long as you're being able to get data, if you're intellectually a little bit like, "Ah," that's what we're going to get to more of today, right now. So if as long as you can get data, that's cool. Um, I will switch the view of the screen in a second. Um, but let me say, I believe where we left off. Oh, and also, I know something has been going on with the Google Cloud or with my head where I know the dates of assignment postings in the Google Classroom have been a little bit wonky, I think. And I think I figured out why. For example, the homework 3 that totally should have been due yesterday. I mean, the homeworks are always meant to be due on a Monday. It should have been due yesterday. I think somehow accidentally it was due like yesterday. It should have been due Monday. I think accidentally it was due Tuesday or maybe even today. That there's no reason for that. That was a glitch. But obviously, when if you handed it in by the time the due date said, then you're fine. Um, but don't infer anything from like you should generally expect that the homeworks are due on Monday, for example. The next one is due Monday, and then after that we have an exam. But that also applies to the game turns. Just to be clear to you guys, I love it that I get to see you in person on Mondays. I really do. But you still, every Monday night, have an opportunity to hand in a game turn that says how you participated that day. Even though we're not on Zoom, you totally can and should do that. I mean, it's optional, but please, like I think there was one that was due 2 nights ago, and like almost no one did it, which is fine. But maybe let me know if there was a reason, if maybe there was a glitch that I didn't see, but I think it was due 2 nights ago at midnight. And maybe or maybe you're just not in the habit when you don't have a Zoom class. It's fine. It's not a big deal if it was one week, but just so you know that, and a lot of you really participated in like all my, rapid fire questions about cosine and this and that. So you definitely can still submit for points even when it's in person. I hope that's clear. Okay, it is clear. Okay, thank you, Lunar. Okay. And if there was a glitch about that due date, let me know like in private chat and I'll do it. But okay. But back to math and physics. Here's where I think we were from last time. Well, very quickly. Like we had this. I'm not redoing this whole thing. I'm just reminding you where we were. I believe, and you're going to tell me if we considered a huge collection of identical harmonic oscillators staggered in phase by a constant amount, right? That's there was other considerations that we incorporated in there, but the basic point. That's not what I meant to do. This is what I meant to do. Yeah, okay. We considered on Monday that you have all these verticals. And part of what I'm not saying here in the paragraph is they're all oscillators that are free to oscillate on one axis while they're being distributed along a different axis. And they're all identical in all respects other than phase constant. They're each starting at a different point in their cycle, but the different point that they're starting in their cycle, we're saying is ultimately a linear function of where they are in the collection, right? Like that's a big mouthful. I'm not saying all that in the right here, but we're saying imagine that you've got oscillators that are free to oscillate on, call it the y-axis, but you've distributed them along call it the x-axis, and you've decided that the phase for any given oscillator is totally determined by where that oscillator is in the arrangement. And it's determined by a linear function, a direct proportionality, right? So we're literally saying each oscillator is increased or decreased in phase by a constant step, right? That's the premise here. And we've decided that once you've done that and you let them all go, what if you stand back and watch what's happening? What you have is wave propagation, right? In other words, right? So like, and when I say wave propagation, I mean like some identifiable, some visual, some identifiable disturbance in an other or from an otherwise equilibrium orientation flows along the, in this case, the x-axis, right? Like you see a bump travel from left to right and from right to left in this arrangement. Even though you see a crest traveling or you see a trough traveling, you see some kind of shape traveling at a measurable, reproducible, predictable speed along the x-axis, even though there is no piece of metal traveling along the x-axis. Like that's our point here. By putting together a collection of oscillators that are very specifically organized this way, oscillators that differ in phase by an amount that depends on where they are in the arrangement. If you put that together, what you have is wave propagation. You have immaterial motion. You have something that is moving in a totally scientifically like analyzable way, but the something that is moving is not an individual thing, right? That's what it's not. So to put it most bluntly, you have a bunch of metal moving here and only metal. And and you see a motion that you can track, but the motion that you're seeing is horizontal and there's no metal moving horizontally. Like that's the bottom line, right? So that's the situation. Sorry, that's the situation that we're looking at. And then we're trying to now analyze the mathematics of that. But we're saying if you organize a bunch of simple harmonic oscillators in a very specific way, you can create a wave motion. Now, in lab, you just created the wave motion, and then you're standing back to analyze everything, like to take all this data and see that the hidden ingredients of that wave that you created were oscillators in space and time. And so in lab, you have the wave and you're like unpacking it. Here in lecture, what I want to show you like right now, or continue to show you from Monday, what I want to show you right now is sort of from the other way around, that we could build up the wave that you're seeing in lab from these mathematical ingredients known as space oscillation and time oscillation, right? So, again, I'll switch the view in a second. So yeah, just trying to get clear here. Stop now in the chat. I believe this white equation that I just wrote. I believe this is what we spent Monday sort of trying to build to, and I think we just got there right before the end of class. Like, did we get to this right before the end of class on Monday?
Yeah, we did.
Yeah. Okay. Thank you for your honesty. They're like, we're going to say yes, but that means he's now going to assume we understand. Okay, good. Thank you. Okay. And that's like exactly where we got, right? Like we basically ended there. Is that fair?
Yeah.
Yeah. Okay. You sound
The
nervous.
last thing I have written down is K is to space as I can't think of the actual term for it, but the W is to time.
Perfect. No, thank you. And thank you for your honesty. And you should submit for double points for that, as should the other people who just use their voice, like Nadine and I think Mohammed. Yes. And okay. So yes, perfect. Okay. The other thing that you're not remembering is omega, but perfect. Thank you. And by the way, okay, no, I'm not going to rabbit hole. Am I? Yes, I am. Do you understand that, like, if Lunar put that in an exam, exactly, I'm saying this as a compliment. I don't mean to single anybody out, but just again, if Lunar put exactly what Lunar just said in an exam document, including the part, like, I don't remember what that symbol's actually called, but this is what I'm talking about, and like wrote an hour or whatever, or called it to, like, that would be like extra good, not extra bad. Because that, whether he called that originality or individuality or like non-chat GBT or whatever, like, that just makes it all the more clear that Lunar actually has this thing in Lunar's mind. Like, it makes it all the more clear that that's not just like you get my point. I'm going to go on, but like, thank you. Okay. So yes. Um, okay. So what was said in English is that this new letter K, and it is a new letter, like it is K again, but it's not the same K as in Hooke's law, unfortunately. So that's why I'm writing it with the serifs. This K is known as angular wave number, whereas omega was known as angular frequency. Like, literally, this whole phenomenon does not become a wave until K is involved. Until K is involved, in other words, until we stretched out a whole bunch of oscillators throughout space, we just had one oscillator going back and forth in time, right? We had a particle that was going back and forth in time. It cycled, it oscillated, it repeated its behavior periodically in time. We said all of these things about where it was at any given moment in time. It was a single varied equation. Like you could say x equals a cosine omega t, or then we got more fancy and said x equals a cosine omega t plus phi, or that x could have been a y, like vertical position. We could say y equals a cosine omega t plus phi or phi, where phi or phi was a constant, right? There was only one independent variable when this was harmonic oscillation. Huge bulk of the midterm is about only that, harmonic oscillation. One object whose measurement depends on time. Now we're saying, wait, if you take a whole bunch of them and spread them out in space, and you arrange them in space in a very specific way, now you've got at any given moment, excuse me. What the lab is trying to show you is at any given point in horizontal space, you have cosine function in time. Like, if you make the y as a function of t graph holding x constant, right, which is one of the things you do in the lab, you get this cosine graph. Please understand that cosine graph is like everything else in math that we've been doing for a month. It's just showing where one bit of your long slinky is going up and down in time, right? Like, those bumps are bumps in time, if you know what I mean. And so we're saying one little section of your long slinky in the lab is acting like its own little individual spring going up and down in time. But then what you're also saying in the lab is, hang on, it turns out if we pick any moment in time, and we stand back and look at where the spring is, where the height of the spring is as a function of horizontal space. So if What I'm saying, and I'm going to move. Oh, sorry. Is KX? Wait. Good question. I'm going to pause for a second. Sorry, that was like 2 minutes ago to chat. Wait, this is a good. Just to clarify, is KX the phi or just K? Wait, that's a really great question. All right, so someone's asking in the chat, just to clarify, is KX, so back to this, is KX the phi or just K? Right, if anything, so sorry, I'll get back to what I was saying in a second. So someone's asking, like in this equation, well, this whole thing, KX is phi, the whole thing, i.e., that's a really good question. The whole thing is phi, by which I mean to everybody, the whole thing is measured in radians. The whole thing means, like the whole thing of KX means where in the cycle a given spring, a given oscillator is. Like the whole thing might be zero, which it is for the very zeroth oscillator. And if in that case, for the very zeroth oscillator, the oscillator that's on the y-axis, that oscillator has a kx of 0, therefore a phi of 0, meaning that when t equals 0, when we started the whole experiment, it's up there at the amplitude position. But then the next one, the first oscillator, like, right? So this is like 0, this is 1, 2, 3, 4, etc. The very next one, the first oscillator number 1, it had the whole thing, kx would be, so x would be 1. So kx would be pi over 2 times 1, meaning pi over 2 radians, meaning that guy, when t equals 0, was at pi over 2 radians, was at a fourth of a cycle in already, was at the equilibrium position. I'm really into this question. I will move on in a second. But what I'm really trying to say, therefore, so in other words, KX as a package means phi, because what we're saying, the new advanced idea that we're saying is there's a different phi for every X. KX is like a rule, like literally you could make a graph where X is here and KX is here, phi is here. Meaning, if you want to know what the phi is for any given oscillator, you plug in the X. You say, oh, I want to know what the phi is for the fourth oscillator. So you plug in 4 for X. You look at the fourth one, and what do you multiply 4 by? You multiply it by K. Let's say in this example, this picture, K would be what? K would be pi over 2 radians per meter. This is why I'm excited by this question. Like, and honestly, to everybody else, I'm not off the topic right now. Like, I was going to like sort of do this my way anyway, but the question makes it much more clear how to do it. Like, K is some number of radians per meter. Let's say, for example, pi over 2 radians per meter, which means it's a rule that's telling you for every next meter that you look, or for every next oscillator that you look in this picture, increase the phi of that, give it that much more of a head start of pi over 2. So it's pi over 2, in this case, radians per meter. In your string in the lab, your slinky in the lab, you can't see individual springs by this. What I'm trying to teach everybody is that you could make the situation, and we used to do this actually in lab 4. You could do this with a whole bunch of springs, and it would have the same effect as you standing in the lab and just shaking your slinky. When you shake your slinky, each little piece of it is acting like one of these vertical oscillators. So the K is radians per meter. It's how much more of a phase delay there is in each next meter. And then you multiply that by the number of meters to get the whole number of phi. So when we first learned about phi, it was just a constant number for a given oscillator, like where it is. Now we're saying it's not a constant anymore. It differs from position to position. Phi does. So phi equals like K times X. I'm going to pause for a second. Does that, so direct chat person, like I'm not, like you should totally get points for that question. Can you just tell me though in the direct chat, like did that answer it? Or I probably answered it like 20 minutes ago, but like did that answer the question? Okay, okay. You're welcome. No problem. Okay, okay, okay. So back to where so yeah, therefore, like if you look down here now, so K is to space as omega is to time. Like I'm saying now, oh, okay, what I was saying here. So what you're trying to see in the lab is that if you pick one spot in, so now we're saying for the first time ever, we have now a function of two independent variables, X and T. You want to know how high a mass is or a piece of slinky is? You need to specify two things. What time are you looking and where are you looking? Y is a function of both at the same time. So you're stripping apart your wave data and you're first making a graph where you pick some X and you ask, what is Y doing as a function of time? You'll see that Y is a cosine graph of time if you pick some X. But similarly, if you pick some T, if you just look at a snapshot, a frame of your lab, you would see that Y as a function of X for any given T is a cosine graph, right? You're taking time cosine oscillators and spreading them out into a cosine space. You have to have both to make this a wave. A way to think about a wave, I'm going to move on in a second, but I'm trying to say, here's the key. I don't know how you write this down, but in lecture, what I'm saying is take a bunch of time oscillators and spread them out and arrange them in space in an oscillatory fashion. Take a bunch of time cosines and spread them out, arrange them in space in a space cosine, and you have a wave. That's what I'm saying in lecture. In lab, you're doing the reverse in a way. You're saying take a space cosine, take a spring that for what in one moment looks like this, but now shake that cosine back and forth in time. So you've got in a cosinusoidal fashion, cosines in time superposed onto cosines in space gives you a wave. That's what we're trying to say. Oh, sorry. Okay, cool. Got it. Okay, okay. So that's why, in lab, you're getting two different cosine graphs. And now, yeah. So now, if you hold, so I'm just repeating this again, but I want to show you something. If you look at one particular horizontal position, you look at one particular horizontal position and look what's happening to the Y values in that horizontal position. And that's called not allowing multiple positions per frame. That's when you have the checkbox off. If you look at that, you see something like this. Whoop, at the end of the day in the lab. And as you already know from like the rest of the homework and all this kind of stuff, this interval is called T. Like the interval between two successive peaks in the motion. Like the duration of one cycle is called T, the period. And so the number of full cycles that you do, so omega is the number of cycles you do per period. You know this already in principle. But now I'm saying, and that's harmonic oscillation. But now if you spread this out in space, as you're doing in the lab, and you get this other cosine graph. Sorry. If you, at any given moment, sorry, now this is for any given moment, any given snapshot. This is one moment of time, right? Well, then the interval between two peaks here, the interval between two peaks here, the interval in is an interval of space now. The interval in space between two peaks, the length of a full cycle in space is called the wavelength. You've heard of this before. You've heard in 10th grade, you've heard in chemistry classes, you've heard in 6th grade. This is denoted with a lambda. This, sorry. Well, yeah. Lambda, that's a Greek letter also, stands for wavelength. Period. I'm running out of space. T is the period. That's the amount of time for a cycle. Lambda is the wavelength. It's the amount of space of a cycle. So period is measured in seconds, but lambda is measured in meters. Lambda is just that, literally the length of the wave. Of the whole wave? I don't know what that means. Of a cycle of the wave, from peak to peak or trough to trough. That's what lambda, the wavelength, is. And I'm saying, when I say in English, angular frequency is to time as angular wave number is to space, I really mean it rigorously. I mean that this number k is 2 pi over that space. It's cycles per space rather than cycles per time. So if angular frequency, so bottom, I'm going to move on. But like if you were just, and I know for most of us, we were like just starting to get our mind around omega. Many of us still didn't like even know what letter of the Greek alphabet is, which is fine. But we were just starting to get our mind around omega. And one way to understand omega is like, how many wiggles are there in the cosine graph? Now I'm saying there's this new thing called K, which can be confusing at first. And if you're at all confused thinking, wait, I thought omega was the number of wiggles in a, like how rapidly the wiggles come in a cosine graph, how squashed the ripples are, you're right. And if now I'm saying, yeah, K is that also, you might be confused. But what I'm saying is omega is how many wiggles there are in the cosine graph as long as you're cosining as a function of time. But K is how many wiggles there are in the cosine graph as long as you're cosining as a function of space. And whenever you have a wave, you have both cosines in time and cosines in space. Angular frequency is how quickly the peaks come in time, and K is how quickly, how densely they come in space. So I'm going to go on now. Both are happening together, superposition. That's what you're looking at the math. And that letter, that letter that I. Okay. Okay, that's a summary of all that I just said. So if that's true, then omega over k would equal 2 pi over t divided by 2 pi over lambda. Like those are division signs, right? And then the 2 pi's would cancel. So we would have like 1 over t all over 1 over lambda. That's the same as like, so it's 1 over t. Well, fine. If you're, dividing by a fraction, you multiply by the reciprocal, right? So if you divide omega by k, what you have is how far it is from one peak to the next, divided by how much time you have to wait from one peak to the next. Like literally, if you're standing away from your lab partner and the ripples are coming in toward you, there might be 3 meters between one ripple and the next, and you might have to wait a second and a half between 1 meter and the next, one ripple and the next. So what does that mean? It means that the ripples are traveling at a average speed of 2 meters per second. I mean, I just divided 3 by 1.5, right? The number of meters between each cycle for each cycle divided by the number of seconds of each cycle is how fast the cycles are traveling along the slinky. I'm saying this is an important point. We're saying this wave, this unthingy thing, is a ripple, a disturbance in the medium that's flowing back and forth, in this case, along the x-axis, right? We're saying there's no individual object actually moving along the x-axis, but every individual material particle object, every little bit of metal is in fact just oscillating in its own neighborhood along the y-axis, right? So each oscillator is doing this really complicated thing that we studied in homework 1. Like it's getting slower and slower and then faster and faster and faster and then slower and slower and then faster and faster and slower and slower. Like it's speed. Each individual oscillator in the y direction has a speed that is changing continuously, or a velocity that's changing continuously. It has acceleration. But what we found out is its acceleration is changing continuously, and its derivative of acceleration is changing, et cetera, et cetera, et cetera. Like harmonic oscillation is this very beautiful but complicated motion where all the derivatives are changing all the time, vertically, like each oscillator. But they're together, they're creating this pulse that's going back and forth on the string, on the slinky. And evidently this pulse has a speed that seems kind of reliable and easier to express. I'm saying once you have the omega and you have the k, you divide one by the other, and now you have the x-axis speed. You now have the speed of flow of the non-thingy thing. The pulse, the crest, the trough will be flowing back and forth through the medium at this speed omega over k. So that's the rate at which, so it's not the speed of the individual pieces, it's the speed of the whole thing. I sometimes call it the propagation speed. The technical name for this is phase velocity. Again, if phase is a portion of the cycle, this is the velocity or the speed at, I mean, it's velocity depending on which direction it's going, but this is the rate at which a piece of the cycle, an identifiable disturbance, like a crest, travels. So, like, if you track a crest with your eye and watch it flowing, it will flow at this very simple velocity. Let me take it a step further. In other words, another way you could put it is, oh, sorry. I think did we already? Hold on, just to see. Oh, yeah. Like I already said, like it's easier to picture. I'm saying that omega over k is the wavelength over the period. And that's an easy way to see it's distance over time. That's what I'm trying to say. So, which I've already said. So that's where I came to the conclusion that it is a speed. But another way you can point, you could remember standard frequency, like measured in hertz. Um, so period is measured in seconds per cycle. Standard frequency is cycles per second. Just flip it right. If it takes you 4 hours to run around the track, then you run 1/4 of a track lap per hour, right? We're literally just saying that. So frequency, if period is measured in seconds per cycle, standard frequency is measured in cycles per second. 1 cycle per second is called a hertz. It's such a standard way of talking about things that it's important to recognize. And it comes up in textbooks and other science classes and web pages all the time. It's important to realize then that speed, we could write as omega over k. We could write it as lambda over t. But in fact, if we really want to write it in a standard way that comes up all the time, we could say that v equals lambda times f. Okay, again, just remember, again, we said omega, f, and t were 3 equivalent ways of describing how rapidly an oscillator cycles. We said, oh my God, we said that omega was the most mathematically direct, period was the most experimentally direct, and f, standard frequency, was like the bridge between the two and therefore was like very standard. Omega, f, and t. If you know one, you know the other two. It seems like we have a jumble of all these different equations that all mean the same thing. We kind of do. But if you know one, you know the other two, and they just have different contextual applications. Same thing here. I'm saying what comes directly out of the math for the speed of a wave is omega over k. But if you rearrange it, you can realize that omega over k is lambda over t, and that sort of makes it more clear that it's space over time. That v is just how far from one crest to the next divided by how much time from one crest to the next. But then you can rearrange that one more time, I'm saying, and you could write it as wavelength times frequency. And from now on, I'm going to write it again. It's a true, so they're all equivalent. Whichever way makes the most sense to you, like lock into that. But they're all equivalent. And the one that's the most common that you see in textbooks and on web all the time, and that gets applied to like instruments in instrumental and stuff, the thing that's really common is this. So I'm just trying to make this, and this is the one you need for the homework that's due Monday. That's also why I'm emphasizing this. Okay. Okay. I'm looking at the time. Okay, okay. So this is technically so I guess I'll put it in English. In other words, okay, so that's what I'm saying right now. For any given wave, the speed of the wave is its wavelength times its frequency. That's what I'm saying right now. That's what you need for Monday's homework. But now I want to go say something else that you really need for Monday's homework. Like, so here comes, I'm making a remark now about this speed. It's super important. It could not be more important for the rest of the course and for life and for the homework is this. So I'm saying speed is wavelength times frequency, but I'm going back to the roots for a second of where I just got that. I'm saying, if you recall, that I got that by saying this. Hold on, let me be even more specific. Okay, what's really important now, slowing down. What's really important is omega, remember, was based on parameters. Like if these are truly masses on springs, part of the reason we've been studying simple harmonic oscillation by itself for like a month is to come to the conclusion that omega always equals something like square root of k over m or square root of g over l or like something. But omega, remember, what omega is not a function of initial position or of amplitude or anything like that. Like, you decide what springs you're using, how stiff they are, how heavy they are, and you put them together, and that determines how rapidly each one is going to go up and down and up and down, right? This is a huge, what we said a week ago, angular frequency is independent of amplitude. That's a crucial feature of simple harmonic oscillation. Look back in your notes or write it any way you want. Remind yourself any way you want. I'm not kidding. Like, what's essential about an oscillator is once you pick your ingredients and you set it, then it keeps time in a manner that does not care about how you started your system. It doesn't matter whether you hold the mass down here or down here or down here when you start, right? Okay. Now, similarly, K is where you put all these masses. Yeah, you could put them anywhere. You could separate them out by, back to the direct chat person's question, you could separate them out by K of pi over 2 radians per meter or pi over 3 radians per meter or whatever. But that's how you arrange. That's how you arrange all of these masses into one big collection of material objects that we then call the medium. So once you fix omega and fix K, once you fix like K and M and the other K, you've now created your medium. You've created a long slinky in effect. And now one lab partner is going to stand at the end of this medium and they're going to shake the medium in some kind of way and send a pulse going through it. What I'm trying to argue here, is since W and K are fixed by the medium, like they could differ from one medium to the next. Like maybe the omega and K are one thing in one lab group's slinky, and maybe the omega and the K are different in another lab's group's slinky. That's fine. But once you're in a lab group and you have a slinky, right? That slinky has a specific omega and a K. Therefore, this is the huge point. It is a huge point. I'm going to do this just to get your attention. Okay, notice the mouth is, I am saying this is a huge point. If you're feeding the cat right now and you're suddenly thinking, did he leave? No, it's the reverse. I am telling you, this is a huge point that you need in life, but totally for the homework for Monday. Let me come back. I'm saying, and let me explain it now. Obviously, I'm going to explain it, but please, actually, I'm really being obnoxious. I know I'm being silly, but this is such a huge point. Can you just give me a quick electronic sign that you're with me right now, like of any kind, just like a thumbs up or like whatever? Thank you, Jalila. Awesome. That's one. Thank you. Oh, that's awesome. I love that. Thank you, Michelle. Thank you, Nadine. Thank you. Thank you, Luke. Okay. Here's what I mean in English. I mean, this is one of the reasons we care about waves so much. And first of all, it's a really cool point. But second of all, it's just like really like important for you to do work. I'm saying if you've ever seen waves of any kind, like go to a pond, look at the ripples on the surface of the pond, like just waves, like normal wave, or go to Coney Island, look at the waves in the ocean, whatever, right? And I'm not trying to be weird, but like go to a bathtub and just like take your finger and like tap at the top of the water of the bathtub and watch the ripples come out. Watch, sit there and watch until you see one ripple overtake another. You know what I'm saying? Like the ripples come out, just any simple wave situation. The ripples come out, they spread out, like maybe they get like quieter and quieter as they spread, but you can see the ripples. Sit there, and if you have some time on your hand, sit there and wait until one ripple overtakes another. Oh, what? You don't have that kind of time? Right. Neither do I. What am I saying? I'm saying, of course, you might not have ever consciously thought this before. I didn't until I did, but you never see one ripple overtake another, right? You could see ripples come from two different directions and cross each other. That you could see. But ripples that are traveling in the same direction, one never passes another. Why? Because they're so polite? No, because they all travel the same speed. Definitely, necessarily, no matter what you do. Like, let's say this now. Thank you very much. Thank you. And I am in fact, if you really think, and this is one of those things you could tell I'm getting excited because I never consciously knew this until I did, but in retrospect, I always unconsciously knew it, just like you, because we couldn't even say the idea of wavelength unless this were true. By saying wavelength, we are presupposing that there's a length between any two ripples, a length that we can like talk about and measure as like a constant number, because there is, because the ripples always stay the same distance apart from each other, always, because they all go the same speed, no matter what, which means even, let's go back to the lab now. Even in the lab, you could say, okay, whatever, Yaverbaum. I'm really glad like that you're yelling, Yaverbaum. But like honestly, in the lab, obviously I can shake my string like fast. And like I even made all these bumps in my string, whereas the lab partners down the hall were just going like this, and they only had a couple of bumps in their string. Exactly. If you go really, really fast, what you're doing, you can do that. You can make a really high frequency wave. You can make I'm going back to I'm going to this now. You can make a really high frequency wave. But if you make a really high frequency wave, necessarily you get a lot of bumps. Your wavelength goes down if your frequency goes up, right? I mean, of course, it sort of seems like an of course, duh. Like I always knew that. If I go like this, I get a lot of little waves going, I get a lot of little waves per unit time and space. Whereas if someone just goes like this, they get very few big waves. Yeah, exactly. Because the frequency, when you say if the frequency goes up, the wavelength must go down, which I am saying. And if you're like, well, yeah, duh, that's just like inverse proportionality. Like I see that in the equation. If F goes up, lambda must go down. Yeah, but that's only true if you assume that V is constant. That's what inverse proportionality means, right? F could go up and lambda could totally stay the same if we're willing to hold, like F equals MA. A can go up with M staying the same as long as F goes up, right? Or Y equals MX plus B. X can go up and Y go up as long as M stays the same. What we're saying here is what will always stay the same for a wave is V. V will always stay the same. Literally, no matter what, it doesn't matter how so this is like when we said with an oscillator, it doesn't matter where you hold the mass of the spring, it's still going to go like, 15 centimeters or 45, it's still going to go, it's either going to go 1 Mississippi, 2 Mississippi, or it's going to go 1 Mississippi, 2 Mississippi. The amount of time will always be the same regardless of the space. We're making a similar point here, not literally the exact same point, but a similar point that's built off that point. We're saying once you set up the medium for a wave, once you say, I'm going to send immaterial pulses flowing through back and forth, this long slinky, it doesn't matter what you do with that slinky, go like this or go like this, each pulse horizontally will always flow at a speed that is fixed and relative to the medium. This is one of the other reasons we love waves so much. Waves make physics a lot easier in a weird way. Like acceleration, gone. We don't care about acceleration anymore once we're looking at wave. I'm serious. Predictability, high. Why do you think? I'm sorry, I'm not yelling at you. I am yelling. I'm just trying to wake everybody up. But like you've heard of the speed of sound. You've never heard of the speed of a baseball. I mean, there's speeds of like baseballs go speeds, right? But different baseballs go different. But a baseball could go any speed. It depends who throws it. Waves, no, it doesn't matter if I'm shouting at the top of my, it doesn't matter what I'm doing right now, even if I run at you. Sound comes out of my mouth and travels through the air at a speed of 340 meters per second relative to that air, no matter what I do. This is one of the, because of the logic we just said. Once you fix the air, once you say it's air at standard temperature and pressure, the air molecules will jostle, will vibe, will oscillate, will send a pulse through that air at one fixed speed that no one can do anything about. That's really something, I think. Now, what, and we still have 15. Okay, wait, hold on. So now I just show you there's mathematical implications of, I mean, there's all kinds of it. So again, this is a big feature that distinguishes wave motion from particle motion. Wave motion is real. It's a real motion of something that's not material. But then once we believe in it, or once we understand it this way, wave motion has properties that particle motion does not have. And one of the key properties is this constancy of speed relative to medium. That opens up a whole universe. I mean, actually, literally, it opens up a whole universe. So wait, I'm going to pause for a second. I'm not asking you to understand like what this has to do with your homework yet. I mean, that's what I'm going to show you in 13 minutes. I'm going to show you like why this has to do with your homework and stuff. But do you understand the words that I'm saying? Like, do you hear what I'm saying? That once you have a wave, you fix the speed of the wave. I mean, once you have a wave, once you have a medium for waves, by fixing the medium, you fix the wave speed. In fact, wait, before I even ask you for clear on that, let me just say it one more different way. Like, say you're just making ripples in the, I'm saying I'm saying the wave speed is fixed by the medium. So the medium could have complicated features to it. Like if we're sending waves through water, maybe what we're treating each water molecule like a little spring. What's the, just like you did in homework 3, we're saying weather can act like a spring. It isn't literally metal, but the values go back and forth in the manner of a spring. So like in homework 3, you were asked what's the effective stiffness of this weather. We were not saying there's literally a piece of metal there with stiffness, but we're saying there's some feature of the weather that's acting like the K of a spring. Similarly, when you send waves through water, you're saying all the water molecules are vibrating back and forth like metal. So the feature there might be like how deep the water molecules are. I mean, that is one feature. Or even how salty they are. That's a feature. So, I mean, if you, you different bathtubs will have different wave speeds and etc. But once you fix the features of the bathtub, you fix the speed of the wave. Okay, wait, does that sort of, we've got 12 minutes. Does that sort of, can you give me an electronic hand if you at least understand the word? Thank you, Lunar. Okay, awesome. Okay, so now what does this have to do with, and thank you, Nadine. Awesome. And thank you, Mohammed. And thank you, people that have really updated. And thank you, Dashen. Okay, awesome, awesome. Okay, so okay, what I'm saying is that the speed of a wave is fixed, constant, relative to the medium for that wave. So this brings us back now to the relative character, the relational character of motion. This brings us back to Galileo's principle of relativity, which we emphasized hugely last semester, or at least those of us who had me, we emphasized it hugely because because it permeates all of the rest of physics. It always comes up that velocity. So recall, I'm saying. Just to remind you, and especially if you didn't have me last semester, whatever, the whole thing about velocity across the board in physics is it's a comparison between two objects. It's a relation between two objects or two perspectives, reference frames, if you like. It's never, and this is like a big thing to get our mind around, velocity is never just a description of a object. Like unlike mass, where like literally a object could have a certain amount of mass or a certain amount of temperature. No object has a certain amount of velocity. It's always a velocity compared to some other object, like always. And there's a million different ways to say this, as we decided in Physics 203, like a million different forms of this idea and a million different implications of this idea. It is the central idea of physics, like honestly. The version of this that we want to use here, so I'm going to, this is a reminder for some people, maybe this is slightly new to some other people, the version, the form of this idea so I'm sort of skipping. So technically now this is like review of last, but if you're given three objects, A, B, and C, we're saying the velocity. Now I have to say this sort of quickly because again, and by the way, again, this is one of those things. Am I really believe? So I'm going to say something I said last semester to those of you who had me. Am I really believing in my heart that just because I said it last semester or just because you were tested on it, does that mean I feel like you're walking around with full command of this idea? Like, no. Don't worry. I'm not assuming you have full command of this idea. I'm assuming like anything else in school, you get better and better at an idea the more you deal with it. And like anything else in school, what's the real secret purpose of Physics 204 in a way is to finally get us all to really grapple with the ideas of Physics 203 and so on. Like, I mean that I'm going to move on. We have 7 minutes. But we're going to have to use this idea in a big way. This is not a test to find out how good you were with it last semester. It's saying the reason we had to work through it last semester so that we can really use it now. So the idea is, I'm saying quickly, but yeah, I'm also saying like take out your notes from last semester and talk about this with one another. I'm saying if you have three objects, A, B, and C, or three reference frames, A, B, and C, the velocity, say me, a subway, and New York City streets. The velocity of me relative to the subway plus the velocity of the subway relative to New York City streets equals the velocity of me relative to New York City streets, always, right? And that example you all know from life. And take it to the limiting case, the extreme version. If I am standing at 0 relative to the subway, if I'm just like standing there, I'm going 0 relative to the subway, but the subway is going 100 miles an hour relative to the streets. 100 plus 0 is 100. Therefore, I'm going 100 miles an hour relative to the streets, and and that's why I take a subway, right? But if you try all kinds of more complicated numbers or even angles, it still works. Like if I'm right, like if you throw a baseball off the subway at 50 miles an hour relative to the subway, then the baseball is going 150 relative to the streets. And if you throw it backwards, then you put a minus sign in there, etc. Right? Like think about that on your own. But that's what I'm saying. Velocities add in this way, right? Now, what's this got to do with waves? But and remember, I warned you. I mean, like on Monday, I mentioned what you want to use. The homework is not easy, but it is repetitive once you get the point of it. The homework is going to ask you to use this idea plus the idea that I've been screaming about, this idea. But now what I'm saying is when we say that V equals lambda F, wavelength times frequency, what we mean is the velocity of a wave relative to its medium equals the wavelength of the wave relative to its medium times the frequency of the wave relative to its medium. I am saying with 4 minutes left, I'm saying relativity still applies. So you can have a situation, you can have somewhat quickly, I'm going to say sound is a wave. Sound is a wave. It travels at it's a wave through air or some other medium like water, but generally air. It travels at a certain fixed speed relative to that air. And the frequency of that sound wave, and you might want to write this down, we experience as pitch or note. Like if the air molecules are vibrating at 440 cycles per second, we experience that in our ear as the middle A of a piano. Or if they're 256, it's middle C of a piano. Like literally, the frequency numbers are notes, are tone, or pitches that we hear in our ear. Okay? If I'm a motorcycle blaring my horn, a sound comes out, like a frequency comes out of my horn, say 256, middle C, okay? If and it goes that through the air and goes to your ear. The thing is, if it goes at a certain speed, 340 meters per second relative to the air, no matter what we do. But if you're moving toward me while that sound is coming to you, the sound is going 340 meters per second relative to the air, but you're going at a certain speed relative to the air, which means from your perspective, the air is going at a certain speed relative to you. So the sound always goes a certain speed relative to its medium. But if you move relative to the medium or I move relative to the medium, then the sound, then one of us is going to measure a speed of that sound that's different from the other and different from what the medium would say, right? Because of relativity, you can send a wave at one speed relative to you, but have it received at a different speed relative to the receiver. It's always doing the same thing relative to the medium, but if somebody has motion relative to the medium, they'll disagree on speeds. So what? Well, and here's the point for the whole homework, they'll disagree on speeds, but the wavelength of the wave everybody must agree on. I mean, if there's 3 meters between each peak of the wave, you see that, I see that, there's no way to disagree on that. Therefore, we're going to get different. This is the Doppler effect. We've got 1 minute. Please write this down. The Doppler effect is if the source or the receiver moves at some speed relative to the medium, then the frequency of the wave relative to the source will not equal the frequency of the wave relative to the receiver. And this is why you hear when ambulances pass you in New York City or like whatever, when cars, motorcycles, horns, If something passes you, if something's coming toward you, you hear one sound. When it's going away from you, you hear a different sound. Both of the sounds that you hear are different from what the person making the sound hears. This is the Doppler effect. When a source of, and I see it's 1040, when the source of a wave is moving differently from the receiver of a wave, then they are going to experience different frequencies for that wave. That means different notes, different sounds, and they're both right. It's relativity. How do you do the homework? I'm going to say, I know we're done. Like if you got to go, but I'm just going to say the homework asks you to figure out the different frequencies for 4 different cases. The 2 equations to use are the ones that I've been saying all class today. These are the 2 equations to use. The technique, and don't look up some Doppler formula on the web. Like you could do that, but it's just going to make life worse. Use these 2 equations and go carefully. My trick, if you're still listening with me and you can tell your other friends, pro tip, what the way to do this is solve for the wavelength according to the source. You'll have all the information to do that. Solve for the wavelength according to the source. Believe that the wavelength is the one thing that both the source and the receiver will agree on. They will. So solve for the wavelength according to the source, then use the wavelength according to the receiver to solve for the frequency according to the receiver. You're just flopping back and forth between these 2 equations every time. But if you focus all your attention on the wavelength and assume that the wavelength is the one thing that source and receiver will agree on, you will get different answers for each different frequency. And that's the point of the problem. I mean, it's a lot, but that's it. Okay. So I'll hang out for a second if anybody has questions, but you have everything you need to. Okay. Have a good day. Yes. Have a good day. I'm going to stop the madness. Have a great week. Oh, no problem. No problem. Got you. Yes. Have a good weekend. Wait, I'm stopping the recording.